What is energy?
Energy is not matter. That's like the best definition. You have E equals mc squared. You can either have matter or you can have energy. It's really about motion.
Energy is the basis of everything you touch, everything you do, everything you eat. Energy is the building block of life.
Energy is, in my opinion, the fundamental cost of the universe. Basically, almost nothing in the universe has genuine cost, right? You can always find more matter, you can always find more materials, you can reuse resources. Energy is like the only thing you can't reuse. And I think it's the only single-use resource in the universe.
Energy is a way of thinking about our ability to direct forces of nature to do things that we might want or that improve our lives. And so energy comes in many forms, and it can be converted between those forms, but it's never created or destroyed. It is merely interconverters.
Energy is a conserved property of the universe that measures work.
Well, I mean, it's essentially the electromagnetic spectrum, like light or radio waves, which are all the same thing at different frequencies.
Because forces are transmitted through solids with electrons and electric forces. The only force of energy that's not strictly electrical is gravitational potential energy or nuclear energy, which is a separate issue.
The simplest way to think about it is it's a measure of how stuff happens.
If you want to talk about energy, you need to talk about power. Power is the ability to do work, whereas energy is a stored power.
But the ability to do work means the ability to change things, to do things. That's been just at the foundation for everything we do.
And so when we think about what it means to create access to energy, what we're really talking about is access to prosperity, access to abundance. Energy is required as an input to every raw material. Every material, every chemical has a series of chemicals and materials that came before that, all of which were arranged molecularly by heat. And so we are constantly putting electrodes into things and burning things just to rearrange molecules, first on a raw materials basis, but then as we increase their complexity from those raw materials into processed goods, energy goes in every step along the way.
The main effect on our daily lives and our future economy will be the provision of electric power, a new source of industrial power.
It is not too much to expect that our children will enjoy in their homes electrical energy too cheap to meet.
So civilization continues to find better forms of energy and better ways to utilize those forms. You can basically track the standard of living and just the general wealth of society based on how much energy that it uses.
Simply as you think about the advancement of society, it's just access to more available and cheaper energy sources. The more that humans can consume energy, the more productive we become, the more prosperous we become, the more things we can invent, the more people we can have on planet Earth.
If you track any metric that people track of quality of life, it always gets better with energy usage.
Looking back at history, you would see every civilizational unlock or transformation of how society functioned based on a new source of energy or increasing the kilowatt hour per capita, which is directly tied to GDP per capita over time.
There's something called the Human Development Index, and this is looking at basically human outcomes across GDP per capita, education levels, longevity, and you'll see that these are directly correlated with energy access.
So one of the nice things you can do if you look at, say, GDP or total factor productivity graphed over time, going back to the earliest historical economic records we have, basically very flat growth for most of history.
And there's a really fascinating book on this, one of my favorites by J. Storrs Hall, Where is My Flying Car? And he actually calls this relationship between GDP per capita and the increase in energy consumption available to a civilization over time. He calls it the Henry Adams curve.
One of the things that I found when I looked at the energy use per person since the beginning of the Industrial Revolution, the energy per person increased about 3% a year over that entire 200 100-year period in a nice, beautiful, even regular, trustable curve.
Because energy is not usually like a final good, it doesn't actually get counted in GDP. GDP is a metric of like final good, so it's an intermediate good in the creation of other things. So a lot of times economists would look at the value added from energy. From the data, it seems like energy punches above its weight in terms of, we get a lot more value out of it than we actually spend on it.
We can do work with our muscles. We can pick something up and we can lift it and create a change. But you can also use electric power to do that, or even heat to make a change happen. And humans learned really early on to take wood and start a fire and use that heat to cook, to do mining. That's really what made us into humans. And if you took away an ability to make fire, like entirely, or to use electric power to spin a motor, we would just have our muscles only again.
So when we talk about humans having a higher standard of living over time and living better and longer lives, we're basically just using more energy. That's fundamentally what's going on. You're using more energy to do more with less, and to do more with less in terms of human capital too. We work fewer hours and we get more out of it. We can experience more of the world. We live longer. We have access to better medical care. That's basically one-to-one with more energy usage.
Our animal ancestors becoming humans it's at that moment of mastering fire, understanding how to control it, how to release the stored form of energy in wood. We then went from that to finding this other energy source. We could make charcoal, essentially, early on. We were able to collect gases off of coal and charcoal also, but only in like the 1800s did we really master that as a technology. And then there was an era where we understood these hydrocarbon fuels.
The agricultural revolution was essentially figuring out really good solar panels. You can kind of think about it this way. Crops are basically solar panels, and they absorb solar energy, they build it into a carbohydrate, right, which humans are able to consume and use for energy. And that really unlocked human flourishing, right? We had enough food to feed everybody, and we could then go about our days, a little bit more of our days, right? We were still working long hours to be able to eat, but we weren't spending all of our time just hunting and gathering.
Things changed dramatically once we were able to access hydrocarbons.
The equipment on farms that uses fossil fuels as its fuel so that you can go run a plow more efficiently. You're not using horses. You can use all sorts of processing equipment that you don't have to use human labor. So it's just amazing how it's just transformed all corners of our society.
The big thing happened when people realized that you could use the power of burning coal. Coal was a considerably denser and more efficient fuel to use.
You're no longer limited to the sunlight you could capture at that time. At that point, you're capturing sunlight stored for millions of years. That's when economic growth really took off, was when we were able to start accessing that level of energy density.
1 horsepower actually is a lot less energy, or a lot less power than 1 horse can deliver. But James Watt invented steam engines, and he was selling steam engines, so he defined a horsepower to be equivalent to a very weak horse after a long week of work. As soon as we had steam engines, we could use steam power to industrialize the destruction of forests and to industrialize the extraction of coal, which could also be used to burn. So it's kind of this feedback process. Well, that feedback process, almost overnight, changed TFP growth, that is total factor productivity growth, changed GDP growth, and all these factors kind of fed into one another and created this kind of accelerating improvement in terms of just general quality of life.
People in the countries where the Industrial Revolution happened, income went up by a factor of 100. Lifetime expected at birth doubled.
A lot of human labor to more and more machine labor, because now you've got this fuel form that's easier to access, that's easier to transport. Some of these really early factories have like a giant motor that operates and turns like a huge gear, and there's a ton of like pulleys off of the system, and that machine will be doing whatever the human task was.
The founders were people who really thought toward the future. They thought, we want to build the foundations here for a country that can support, liberty and justice for everyone. And it's really important to remember that, like, in some ways, energy production is not super prestigious, but actually primary production is what made this country rich in the first place. And primary production is the thing that China is currently massively outcompeting the United States on. Primary production is the wellspring from which all our other forms of wealth grow.
To understand the possibilities of a hyperabundant energy future, we need to start in the past, because the past will show us how we got here and thus how we can get there.
The next really big aha moment was actually that there are big blocks of chemical energy underground. And it actually started out with peat, these composted chunks of biomass that slowly get turned into sort of a burnable form. And peat started getting burned in ovens, and it was used for cooking food, which actually helps that food to become more energy useful to humans as they consume it. We used it to start doing other things like making tools, and those tools can help us till the earth faster, those sorts of things. And then the next big one was coal.
Coal is a kind of rock. It's actually a form of solar power because it was laid down by ancient forests that spent many millions of years growing and then falling over. And so we just have these insane coal beds worldwide of like ancient forests that grew and fell over for millions of years. Today, as a result of like geological processes, it's essentially pure carbon, often with a little bit of sulfur or something mixed in. And we can just dig it up and burn it. And digging up and crushing up soft rocks is about $10 a ton. So that's a pretty neat trick.
That really unlocked the steel age, and it unlocked transportation via trains and all these sorts of things that we didn't have access to before. And at each of those points, our standard of living just massively inflected.
I think it was in the 1700s roughly that basically extremely inefficient steam engines were used to pump water out of mines. So in Cornwall, which is the southern part of Britain, there are mines mostly for tin, which is used as an alloy of copper to make bronze. And there have been mines there going back thousands of years. We know that the Phoenicians, we know that the ancient Egyptians traded either directly or indirectly to get tin from southern Britain. And we also know that the Cornish miners were so expert at what they did that they became the diaspora all around the world in the 1800s that taught the rest of the world how to mine. So for example, California is full of all kinds of mines. Those mines were often found and staffed engineered by Cornish miners, the ones who survived, the ones who knew how to build stopes and blockade things and so on. And like they would dig these mines underground, below the water table in southern Britain, and then out under the ocean. So they're mining like up to a mile offshore through rock under the ocean. So these initial steam engines were used to pump water out of the mines. How does a steam engine work? Roughly, it's basically determined by how hot you can get the hot side and how cold you can get the cold side. And that the temperature spread is what allows you to extract mechanical energy. And for practical steam turbines stuff, it's in the 30s, maybe the 40%, low 40%, which is respectable. But easily 60 to 70% of the energy is going out as heat. Once had steam engines that could keep on feeding coal in. Basically, this kickstarted the Industrial Revolution.
Oil, black gold, I think really took humanity by storm. Like this made the modern world. And I think to a degree that people don't appreciate. It's not just the fact that we have, diesel and gasoline to drive cars around. It also made the material reality of the world different. We have plastics and we have all of these, materials that we build the entire world out of. If you look around any room, I think most of what you're going to look at with your eyes is essentially built out of hydrocarbon.
Well, I'm just thinking about like the chair I'm sitting on has some sort of plastic component in it. That's made from oil.
And the ability to actually have a liquid store of energy is very underappreciated, I think. The fact that you can hold energy in a bucket and you can take it from place to place is a massive unlock for humanity. That means that we can fly. It means we can drive long distances in a car that anybody can own. Anyone in the world can purchase a vehicle, even if it's just a small scooter, and they can get miles and miles where it would have taken, weeks before. Oil is one of the most interesting substances in the universe, actually. So if you look at the periodic table, I actually would challenge you to find a better substance than oil for just carrying energy around. And the reason for that is that it's oxidizable. So we have oxygen in the atmosphere, which means we have 1/2 of an oxidation reaction just waiting to happen. And then it turns out underground there's the other half, right, which is a hydrocarbon. And when you mix hydrogen and carbon with oxygen in combustion, you also get pretty clean elements as well. You get water and you get CO2, things that are already in the atmosphere. And that oxidation reaction, it turns out, carries an enormous amount of energy. You can put that through a pipeline. You can still put it on a train if you want to, but loading that into a pipeline and moving it across states with essentially no logistics at all, that's something that was only unlocked by oil.
And part of this history is like that Standard Oil created the Industrial Revolution. Standard Oil, right, is this company which their goal, their mission statement is that they want to produce the highest quality oil at the lowest possible price to the customer. And so around the turn of the century, the company's formed and starts operating and they start massively expanding. But as they're making profits, they take all the profits and put it into R&D, and they buy up these assets where somebody has drilled for oil. And if you drill for oil, you either get sour or sweet crude. Sweet crude is low sulfur, is ready to go right into a motor or engine or transmission, and it won't damage the metal. And a sour crude has high sulfur and basically can't be used, and no one knows how to use it. So they hire these scientists, run all these laboratory experiments, and they basically sit there and for years work on a solution. Meanwhile, the company just continues to buy up all the sour crude that no one else knows how to use. So it's pennies on the dollar. And then eventually just have this massive breakthrough and unlock it and go, well, we now have a chemical process. They basically developed one of the refinery processes.
America and oil have always gone together in a really special way because of the long fascination that America has had with moving things, right? We love things that move. We invented cars, right? And we wouldn't have been able to invent the car without something to put in its gas tank. We invented airplanes, and there's no formulation of an airplane that doesn't work without a hydrocarbon fuel. And these things are just stitched into the fabric of who we are as a nation. Having invented most of these modern forms of transportation that move us around the world, I mean, you can just see it everywhere in America. We love our cars, we love our airplanes. We have this lifelong obsession with them as a nation, and it's definitely stitched into our DNA.
Fusion, every day you wake up in the morning, you're essentially living under a giant fusion reactor, which is the sun. And we've been trying for decades to harness the sun. But what if we can actually artificially create a sun on Earth in a bottle? But we'll talk about that later. This section is supposed to be about solar.
My name is Handmer. I'm the founder and CEO of Terraform Industries. We're making cheap synthetic natural gas from sunlight and air. Solar is a pretty neat trick. The art of a useful energy conversion is to take energy somewhere where it's cheap or not needed and convert it to something where it's expensive and needed. And you can extract value by doing this and pay for the process and pay for yourself and take home a tidy profit.
Solar is nuclear fusion with gravitational confinement and like solid state conversion. You don't need a steam turbine to convert it to energy into electricity. And so that's amazing.
The advantage of solar energy is that the sun is a maintenance-free, long-term commitment, inexhaustible nuclear fusion reactor. It's just 8.5 light minutes away. It's in our local neighborhood, comes up every morning. Essentially, free energy rains down on our heads all the time. And by free energy, I mean about 1 kilowatt per square meter, which is a lot. The form of solar energy that's super exciting to me, however, is solar photovoltaic power. Solar photovoltaic power takes our increasing wizardry with silicon and allows us to use that to directly convert the photons that come from the sun, bang into the silicon, kick some electrons across a diode junction, and then the electrons are like, oh no, I'm out of equilibrium. I want to go back to the other side. And you say, no, you can't do it. It's a diode. So they have to go a long way around through your wire, and you get energy out of that. And the amazing thing about a solar photovoltaic panel is that it's like 20 to 30% efficient, which is almost as efficient as a heat engine, as a steam engine, but it has no moving parts. It costs almost nothing. Last year, I heard that we deployed about 600 gigawatts worldwide, which is more than the total global nuclear fleet in 1 year, which is just, it's a lot.
I think solar, I mean, we've seen it in the data. It's like the amount of what we can achieve now in terms of cost per output has been phenomenal. That learning curve has been absolutely phenomenal. It continues on. So I think there's no question that solar is going to be a huge part of our energy future.
It allows you to take unproductive land, put essentially what rounds to a pane of glass on it, and then it will spit out energy approximately forever at low cost. They're literally machines that you put on the ground and they spit out wealth. So now you have extremely high quality energy because you can easily convert it into other forms. But it's in the form of direct current power, and it's out in the middle of a field somewhere. You still have to get it to the market. You still have to get it to the person with a credit card and make a Stripe payment for the electricity because that's where it's generating the value. You have to get it from where it's produced to where it's needed. And the way this has been done traditionally is you put it into power lines and then move the power lines down the road to people. And along those power lines, you can put some batteries in various places to even out the load and make sure you have power available in the evening and at night. You can allow the price to swing a little bit so that the battery operators make some money, and so that you are able to use price signals to accurately predict how much demand there actually is and how much you should actually build. It's very straightforward. It's completely uncontroversial. There are multiple island nations right now that use solar plus batteries and basically nothing else for power, and it's actually as reliable, if not more reliable, than conventional, gas turbine power plant or a diesel power plant or something like that.
Well, solar has gotten cheap because it's a solid state technology. There's no moving parts. It's pretty simple from a mechanical standpoint. That quality is very associated with falling prices and pretty good learning rates. And as you just increase deployment of solar, the cost of making the panels has come down and come down.
The really incredible thing about solar, though, is that you kind of have a choice. when you put in a solar plant and you hook up some batteries, you get to choose how many batteries you attach, and that allows you to decide how much power you're going to have. The batteries add cost, but they also allow you to use the power more. In concert with that, you basically want to have like a level of economic productivity of your end use. And this ends up bifurcating. It's a foregone conclusion that like solar is going to get extremely cheap in the future. If you can use that power in the field, right next to the solar array, you can get power that's insanely cheap, like well under $10 a megawatt hour. And this is transformational for processes that use electric power to perform fundamental chemical conversions or interconversions in matter. Like I'm talking materials processes. These are the processes that right now emit an incredible amount of CO2. The industries that produce most of the CO2 and so low revenue, you could never have hoped to decarbonize them by like paying $100 a ton to decarbonize, right? The only option here is to say, well, humans obviously need a lot of concrete. They obviously need a lot of steel. They need a lot of these other kind of materials. These materials are extremely energy intensive to produce, which means that we basically use coal to produce them. They're very polluting. Let's figure out a way to take cheap solar, which is way cheaper than coal if you can use it as it is, and then this demand, and say, can we use this cheap solar to give people this fundamental necessity at a better price than they could ever achieve with coal with a low capex process? That's the $1 million question.
I think there's some questions as to how much energy do we want in the end and how much square footage will those panels take up? Are there limits to how much we want to sort of cover the earth with solar panels? And that's a human question, right? That's an aesthetic question. My hope is that we just continue to get more and more efficient with our panels so that you just need less of, again, that square footage question. But no question that will come down in cost. I think batteries, same thing. And they're such a great pairing, the solar and batteries together. So we'll see a lot of electrification come through that as well.
I'm Zach Dell, co-founder and CEO of Base Power Company. Base is on a mission to fix the power grid. We build hardware, software, and deployment operations to install battery technology on the grid to expand our capacity for power consumption and provide homeowners with affordable, reliable power.
So I'm Justin Lopas, COO and co-founder here at Base Power. Before co-founding the company here, I was at Anduril and leading manufacturing. Prior to that was at SpaceX, leading the manufacturing team, working on the early prototypes of the Starship, and even before that on the human-rated version of the Falcon rocket. Kind of where technology and operations meet is typically manufacturing, and that's been primarily my background.
Our energy infrastructure in the US is very old. The grid was largely built in the 60s and the 70s. While there's been a lot of innovation in power generation,
but not enough transmission to get that power to residents across the country. And so there was a focus on building out those transmission lines and that power, and we've now trickled all the way down to the resident.
If you look at the cost of electricity, which is kind of the core fundamental concept that we're trying to lower and therefore have more abundance of energy, almost 50% of that cost is just getting that energy to where it's going. So even if you totally solve the generation problem and you have energy, quote unquote, too cheap to meter, you're gonna still pay a lot to get it to where it's going if the grid is not fixed. The grid is actually the biggest machine in the world, and it is potentially the most complex and distributed machine in the world. Its fundamental job is to connect generators to load, basically supply to demand economically. So the grid was built 120 years ago. Thomas Edison at Pearl Street Station, the first power plant that had distribution to local businesses and homes. And then the grid sort of evolved from that over time. Traditional model of the grid is that it's a one-way street from generator to load, from the nuclear power plant to the home, from the solar farm to the business. That is fundamentally changing, and the grid is becoming a two-way street, and that's something that we're a very big part of. We think that you should have generation and storage co-located with load throughout the grid. This is a far more effective way to use the transmission and distribution infrastructure.
Battery storage is the unlock to the energy transition. It allows us to time shift electricity from times when it's not needed to times when it's really needed. So we relieve those two constraints by deploying batteries where the grid already exists to circumvent that interconnection queue, co-located with the load to circumvent that transmission congestion.
It wasn't that long ago that Elon Musk was roundly criticized as an idealist and a dreamer for saying it would be possible within the foreseeable future for Tesla to produce battery cells under $100 per kilowatt hour at cell level and ultimately the pack level. And last year we saw various different chemistries of lithium and sodium-ion batteries being produced and sold in a number of countries, not just China, for in the $50s of dollars per kilowatt hour, which is, it's just nuts. Like that's off by a factor of 2 in just a couple of years.
If you look at the utilization of the grid, most lines on the grid are utilized under 50%, meaning most of the time they're not literally used to their capacity. You put batteries everywhere, you're now able to reduce the peaks and increase the troughs, and now you're utilizing your grid much more effectively, and you can add much more load. You can consume much more power that way.
So this is a demonstration of what our Generation 1 hardware looks like. So the lights represent the flow of power. So power comes in through the meter, charges up the system directly, and then backs up the home's entire home load. And when the grid goes out, the battery is used to support the home's load. And the lights are on, you keep your fridge running, you keep your AC going, and you're able to use power uninterrupted.
I think it's so important that we have a grid that's accessible to all, the grid is sort of this public good, public entity. But I do think something to be said for rethinking some of those grid kind of rules that we've set up.
There are a lot of requirements that seem to be just for the sake of bureaucracy. And so getting around that red tape, removing it so that we can bring further resources to residents is really a main focus right now. And I don't want to say that it's permissionless innovation. There are definitely checks and balances that need to be in place for safety. So we don't want to go unchecked in these installations. We want to make sure that not only us, but any actor in the space is acting according to all of those safety requirements. But there are those unnecessary kind of extra red tape that when those are removed, we can kind of meet the state and meet the growth of the country where it is.
Nuclear energy is one of the most fascinating stories of technology that we've seen so far. So you have what's called a fissile isotope. A fissile isotope is an atom that's particularly unbalanced and is able to split when you bombard it with a thermal neutron. So a thermal neutron is a neutron in the low energy spectrum. It's moving slow enough that if it contacts a fissile isotope, it has a certain chance of splitting and producing both heat and more neutrons. So the basic concept is to put uranium in a core and start the nuclear reaction. And hopefully these neutrons will contact other atoms, which will split, create more neutrons, contact other atoms, split, and you have a sustained chain reaction.
The interesting thing about American nuclear energy, it was actually born of the Manhattan Project, of our nuclear weapons program.
And this had come off of decades of research around radioactivity, around even just the structure of the atom, how it worked. And we're going right into World War II. So immediately people realize, wow, this is extremely powerful. Can we turn this into a weapon?
In the Eisenhower administration, he had a program called Atoms for Peace.
We've developed this awful technology, but we can also use it for good. And so let's go figure out how to use this technology for good by producing a ton of power. The AEC helped promote that.
So it started essentially in 1938. This is the first time we did actual nuclear fission for the first time. And what's shocking is that to go from the very first atom split in 1938 to the very first nuclear reactor was about 5 years. From brand new science that we'd never really understood before to a machine that can actually utilize that science and create energy was about 5 years.
If you look at the 1960s when nuclear technology is invented and we start to scale it up and build all the nuclear reactors we have in the US, it's 20% of all electric power today. When we did that, we stopped burning oil broadly as a nation in large-scale plants. We just didn't have to do that anymore. And then all that oil went into transportation. Right, it fueled the ability for people to just have a car and drive it around, which totally changed the way cities were designed.
The first artificial nuclear reactor was built in 1942 at the University of Chicago. It's called the Chicago Pile, and it was built by Enrico Fermi in 15 days and turned on the next day. And they just did it like under the bleachers at Stadium.
What is it made out of? It's like wood with graphite bricks that they just stack, and the wood is just holding it together. It has no shielding, it has no containment, and the graphite bricks have these holes in them with uranium fuels rods that they drop down those holes, and they keep building it up and up. They just make it with a little bit of margin beyond where they think it'll go critical, and they have a scram system, which is a guy ready to cut a rope that'll drop a rod of material in that'll absorb neutrons and stop the reaction. And they figured all this out without any rules.
And after that, about 9 months later, we completely redesigned the architecture of it and we produced the X-10, which was really the first gas reactor. And what's interesting about this development is that this all happened months at a time, right? We went from Chicago Pile 1 to X10 in the period of about a year and a half. This is the type of rapid iteration that I think was the hallmark of the 40s through 60s in American development. And by the time we were in the mid-60s, we were producing dozens of nuclear reactors all over the United States, and they were working phenomenally well.
The rules were that they were scientists, that they were careful, they were thorough, they were getting critical review from their peers, but there wasn't anything saying, here's how you build a reactor, here's what you can do, here's what you can't do.
Unfortunately, in about 1979, in the West at least, nuclear came to a screeching halt. That was essentially 3 Mile Island.
The accident occurred here at the 3 Mile Island nuclear power plant, a dozen miles south of Harrisburg. 4 o'clock this morning, 2 water pumps that help cool reactor number 2 shut down. Officials say some 50 to 60,000 gallons of radioactive water escaped into the reactor building. Steam escaped into the atmosphere, and radiation was detected as far as a mile away. At least 50 workers, and perhaps twice that number, were at the plant.
There was no property damage beyond the fence of the facility, and 13 independent studies failed to find any health effects or environmental effects beyond the perimeter of the facility in the surrounding areas. So this is one of those events where public perception is really much larger than the event itself.
The formation of the NRC in 1975 and the 3 Mile Island incident in 1979, I think nuclear regulation has significantly increased.
There was a kind of an allergic reaction to nuclear power after the end of World War II, was worried about nuclear war and missiles and all of that sort of stuff. And it had quite a psychological punch to it. If your school is making you hide under your desk every day for atomic bomb, yeah, you're going to think, okay, this is not a good thing.
I think a big part of why we kind of quickly went from atoms for peace, like people being excited about the future for nuclear power, into this sort of villainization of nuclear power was because a lot of those atomic tests that happened in the late 50s actually impacted people's lives. And we didn't have, we had no tolerance for that. The US military and government was fairly irresponsible in terms of just like testing, the next atomic bomb, like all over the place, having fallout in different places. And radiation is no joke. You don't want that.
So we began to have arms limitation talks and at least cut down the amount of nuclear missiles and all that sort of stuff. And the fear of the nuclear war receded. And all the people that were encrust themselves on a movement and make money out of it were kind of running out of movement. And they figured, okay, we can use the same word, nuclear, to oppose nuclear power, which was a completely different and completely safer sort of thing.
With the environmental movement, with the first Earth Day, with all these things that were happening, that just like quickly took on the anti-nuke mantle as well. It was almost like game over.
So you got this big anti-nuclear movement that didn't really care what kind of nuclear it was talking about, as long as it was something you could scare people with. And again, at the same time, people's concerns shifted from knowing all about technology and caring about it to knowing and caring about other things. The ability of the average person to understand the distinctions between nuclear weapons and nuclear power kind of went down.
Most people falsely assume that 3 Mile Island led to the pause of the nuclear industry. And because of the coincidence in timing between the downfall of the nuclear industry and 3 Mile Island, it has led to this recursive pattern of the more people are afraid of it, the more regulations are added, and then the more people become afraid of it. But in reality, 3 Mile Island, happening in 1979, was a year after the industry had already collapsed, just due to failing market structures at the time. And so what you had was the cancellation of nearly 200 contracts for nuclear power plants in 1978. Then you had 3 Mile Island happen in 1979. And what the nuclear industry discovered at that point was actually a new business model. Now that people were afraid of nuclear, they pivoted. They started selling safety systems, which made them hundreds and then billions of dollars per nuclear power plant. When you looked at the existing base of nuclear power plants at the time, well over 100, this was a huge market to sell into. Every time that there's a tragedy that might somewhat be related to nuclear power or directly related to nuclear power, the industry seizes on that to ratchet up regulations even further.
There was Chernobyl, which was like the real kind of accident. There was Fukushima, which actually no deaths caused from the meltdown itself, but a lot of deaths caused, unfortunately, in the tsunami. And then there was 3 Mile Island, as we mentioned before. All these just kind of served to scare people and just kind of feed into this anti-nuclear movement that was starting to grow. Then the economics piece happened. They're expensive. Then we forget how to build them.
With the public health and safety in mind, we're trying to do a good thing, but you keep adding rules that never go away, right? They don't expire. And so you end up with this like overcomplicated thing where you don't really have anymore what you want. And now a person who is capable and intelligent and diligent and wants to build something great for the world has to go through an unpacking of like 70 years of regulations that like are from before they were born. And so they don't make sense. A set of rules won't consider really drone attacks or like cybersecurity. Like the things I'm actually worried about they're not even in there. And so we have to sort of make up those rules that we actually care about so we get an actually safe system.
What we're seeing in China is remarkably different. 27 reactors in process right now. They are moving quickly. They have a different setup, right? They are a centrally organized, sort of more nationally oriented government, society that can allow you to do these like big infrastructure projects more effectively. What I think the US needs, since it doesn't have that kind of national mandate, we're gonna like federally build these things, is we need to see regulations stripped away. At one point when we had nothing, it was super beneficial, right? It's like, oh, people are thinking about the air pollution they're causing and like, the massive quantities of species they're killing or whatever. We're at the point now where it's gone far too far. We're just hamstringing ourselves. Let's figure out the financial incentives too. Like we want people, this is a capitalist society. Let's get people to be able to make money off of this. I'm actually very bullish about kind of the big tech giants and their interest in AI because they're gonna have to be figuring out where to get their energy from. And a lot of them are oriented towards clean energy. They have, emissions targets they want to hit. And nuclear is just so well positioned, right? It's 24/7, 100% clean. That could be the answer here to how we kind of restart some of the nuclear power plant build out in the US.
It's super interesting because even though Congress said we're going to open this up to make maximum use of the energy that nuclear power affords, and that we're going to not require a license for everything. When the Atomic Energy Commission went to make the rules, they said, no, you still need a license for everything. And so they basically ignored the directive of Congress and they kept a stranglehold on it.
We had a technology that was going to be the next step.
So Radiant's working on a 1 megawatt portable nuclear microreactor that can be mass produced. And the reason it's 1 megawatt is if we made it much larger, you could not easily ship it around on a truck, and you could certainly never put it in a big transport aircraft. So the size of the thing we're working on, we can do both of those things. And what we want to do is make 50 reactors per year so that we get really, really efficient at doing it. And having it be fully portable means you can actually do mass production the first time ever, gives you the highest reliability, the lowest possible cost of construction, right? Just from learning by doing, getting a high rate of production. And when you have a portable nuclear reactor that's this size, we can send it to literally anywhere in the world. And then also very cool, it can just come right back. So the customer, they can have clean nuclear power, last for years, and not have any nuclear fuel on their site. It stays in the system and we just bring it back and handle it for them.
I'm Isaiah Taylor. I'm the founder and CEO of Valar Atomics. Valar Atomics is making thousands of nuclear reactors for heavy industrial power. So data centers, metals electrolysis, and making abundant clean hydrogen. And we'll actually use that hydrogen bonded with CO2, and we can actually make all of the hydrocarbon fuels that currently power the world. I've been thinking about this company for a long time, basically since I was 12 or 13. I grew up thinking about nuclear energy around the breakfast table. My great-grandfather was a nuclear physicist on the Manhattan Project. I knew my great-grandmother for a long time, and we used to just sit down, over breakfast and talk about the Manhattan Project and Oak Ridge and the story of nuclear energy. So I spent a long time thinking about it, and I wanted to know, why did nuclear not scale to be the major power source for the world? And I spent a few years trying to answer that question. I think it's a technology question, it's a politics question, and I think I formatted the company in a way that solves all of the critical problems with it, and it's going to allow us to actually scale for the first time.
I'm Julie DeWahl. I'm the co-founder of Antares. At Antares, we're building microreactors, small ones that can go after critical infrastructure for largely military use cases, but also commercial off-grid use cases.
I'm Jordan Bramble, CEO and founder here at Antares. I previously worked in the White House at the Office of Management and Budget, and I have a lifelong passion for physics and complex systems. Well, the single biggest thing I learned is how the federal budget process works and how large government acquisition programs are led. And it turns out in nuclear, you kind of need that too to get reactors built. You need to be sufficiently technical. You need to understand how Washington works, and you also need to understand how to capitalize a business. So really what makes us different is our approach to this problem. We actually like to call it strategic energy. And what that means to us is using the unique characteristics of nuclear fission to enable things that would otherwise be impossible with other forms of energy. Example of this that maybe we're all the most familiar with is the naval nuclear programs have actually built something like 4.5 times the number of reactors as the entire commercial sector. We don't do that because the energy's cheap. We do it because it allows us to put submarines underwater with nuclear weapons on them anywhere in the world for 6 months at a time, undetected. And if you really zoom out and take a broad view, let's look 10 years into the future, we could be using that same propulsion technology to power underwater autonomous systems, and they could go underwater undetected even longer. Our belief is that a heat pipe cooled system allows us to do both underwater, terrestrial, and space-based use cases.
You have, let's say, remote ground stations, remote missile defense sites, like those need to be 100% working, and they require energy. We know that today our missile defense sites up in Alaska and the Arctic are working off of diesel generators. Not enough, right? You don't want to have something where the fossil fuel supply chain could cause, your systems to be down. These are really important, and I think, deterrence and having your systems at the ready, people know that there are no holes to poke in it. That's exactly what the military is looking for.
My name is Bret. I'm the founder and CEO of Last Energy, and we develop micronuclear power plants for the heavy energy intensive industries such as factories and data centers. We deliver on-site to our customers to serve in a plug-and-play manner. So we offer electricity as a service, but at our core, we're designing a nuclear product. And I say product pretty intentionally, because one of the other challenges that we've seen historically with the nuclear energy industry is costs just go up, 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 while in every other industry, the more you build something, costs go down, down, down. And so the key was switching from this construction project to manufactured product mindset. SMR stands for small modular reactor. It's a class of nuclear power plants that aren't as big as the traditional ones, hence the S in small. Modular means they're trying to use more modernized construction techniques. And when we think about modular, we want to take it all the way to the limit. How can everything be built in a factory and virtually nothing done on site? To us, that's the epitome of what modular means.
When I went to leave SpaceX, it was because the DoD announced a thing called the PLA program.
We are currently in the process of beginning to build the reactor. It is a prototype. It's going to be built in Virginia, and it's going to be tested in Idaho. And the prototype is never going to leave Idaho. But the Department of Defense has to decide if it wants to build more nuclear reactors in the future.
They asked specifically for 1 megawatt or more portable reactors that are under 100 tons. And that's really what set the stage for thinking about this, because I think that the DoD is an entity that can be the first customer, can help fund development, and can help put some positive, constructive pressure on the regulatory structure so that we can build again and deploy these things. So a lot of aspects of the design are frozen by what does that one major customer want? And then we went from that point to figuring out that actually there's a bunch of interesting commercial customers. There are these remote villages and remote mining operations that in Canada and Alaska and other places that could be supported. And so then we went, well, what if we pool all of those customers and mass produce? That's the basic framework for how we got to what we're focused on now.
Well, we're working right now on our demonstration unit, which is our first reactor unit minus the nuclear parts, so minus the nuclear fuel and things. That just says, hey, can we put all these pieces together? Can we get our systems to work? Can we get our materials to function at the temperatures we want to work at? And that first milestone should be hit in the next couple of months. We're really excited about that. And I think that just proves ourselves as a team, right? Being able to work together, build with a cross-discipline team, something that is net new. Granted, all of the materials we work with have been used before, but this sort of combination of it is a new thing. And so we're really excited about this demonstration unit.
Now, there's also a safety principle embedded in this as well. When uranium atoms split, the neutrons that leave are actually traveling too fast to cause more fission when they first leave. And you actually need to slow them down. And the way that you slow them down is called a nuclear moderator. So a moderator is a material that essentially bounces these neutrons around until they're slow enough to contact another uranium atom and cause more fission. And what's interesting is that there's this safety principle baked into nuclear physics. And that is that as moderators heat up, they actually become less effective as moderators. And what that means is that the neutrons stay in fast spectrum and eventually get absorbed into other materials rather than causing more fission, which means that the rate of nuclear fission reduces in the core. And eventually, the core should be hot enough that your nuclear reaction actually stops altogether. And that's a completely passively safe reaction. Now, the only way to take advantage of this principle is to choose a nuclear moderating material that has a very high melting point, because you want that effect to take place where it gets so hot that the reaction just shuts down well before the melting point of the core. And our reactor is exactly like that. We use graphite as our moderator. Graphite has an extremely high melting point, and long before we would get into a meltdown state, the nuclear reaction would just cease altogether.
I want to say it's true that every reactor design is fail-safe. Typically, reactors have control rods, which if you cut power by gravity, they fall into the reactor and it shuts the reaction down. And there's a huge number of them, so they don't even all need to function for that to be true. If you put control rods in our reactor, you have a risk that if there's a high rate of heating of the gas that's inside, that pressurized gas can throw the control rods out. And that has happened in earlier reactor development history. But so what we use instead are these control blades that go in a circle, in a cylindrical fashion around the core. And those control blades can rotate into or away from the reactor and control the reaction in that way. And so they can't be ejected from the system. And then in our design, if you heat up the fuel and the graphite in the system, it will also naturally reduce the reactivity and shut itself down, like render the reactor subcritical.
I think the SMR ones are really, really interesting because there's this chicken and egg problem with the NRC, which regulates nuclear, where you need to show them data that your reactor is safe in order for them to license you to build the reactor, but you can't get the data until you get the license. And so there's this like big chicken and egg problem going back and forth. Companies like Radiant are trying to overcome that by working directly with the Department of Energy and something called the Dome up in Idaho at Idaho National Labs. Some people are going through the DoD where you can test with the DoD and get that data. Some people are going abroad to get that data, but it's this like real big bottleneck and chicken and egg that you aren't allowed to get the data that the NRC demands.
The Dome is a existing 80-foot diameter structure. That's actually this giant cylinder, half of which is underground. It was built in the 1950s at Idaho National Lab and had the experimental breeder reactor 2. And so we're building a reactor here right under the quality program that's been approved by the lab. So we'll do like an acceptance test and then we'll ship it out this door right behind me, but then it'll culminate in this 150-hour endurance run. What we're trying to do is around the clock with 3 shifts of operators, keep the thing running for 150 hours continuously without having to do anything. And that will be a really great proof of reliability of the system. And then we'll go to focus on getting units out to customers and the factory beyond that.
Probably our most fundamental conviction at Valar Atomics is that you actually need to build nuclear reactors in order to build nuclear reactors. And this sounds a little bit circular, but it's actually quite serious. All technologies evolve through actually building things. It's the only way that technology evolves. And unfortunately, in the United States, it's essentially impossible to do that. Our regulatory environment is not formatted in a way that allows entrepreneurs like myself to quickly build a small reactor, test it out in the desert, and see if it works. And this is the only way that advanced technology moves forward. So as a team, we got together and we said, where's the best place to build a nuclear reactor today? And we chose the Philippines. The Philippines has been an incredible partner for us. They're eager to build. They want to see nuclear happen in their country. They really need it. They're an archipelago nation, 7,000 small islands spread throughout the South Pacific. And they need nuclear in order to thrive as a civilization. And so they're willing to work quickly with us to go through the R&D necessary to bring nuclear back.
I think there's going to be a winner-take-all approach, but I don't think just because of the CapEx intensive nature and the supply chain intensive nature that it would be possible for a single entity, a single company to be a winner take all in the sector. I think you're going to see one company, I hope it's ours, break through with a model that shows the successful economics, that shows repeatability, that shows scalability. And then you'll see a lot of fast followers into that segment. And over time, then it'll be a different type of competition. It'll be a competition over market share instead of race to who's first. Potentially, for the first time in human history, if we're able to really take nuclear energy and realize its full potential to fully decouple environmental impact from the energy source itself, and therefore create a world of abundance without consequence.
Fusion is the process that powers the sun and all of the stars in the universe. So you could almost say that fusion is like the universe's choice of preferred method of making energy.
It's the simplest form of how the universe works. So taking the simplest atom that's most abundant and creating the conditions for it to fuse, which means for two hydrogen atoms to combine together. And the famous Einstein E equals mc squared equation, if the small mass of mass is lost, multiplied by c squared, which is the speed of light squared, which is a very large number, you can release a significant amount of energy. I think without fusion, the whole universe would be just a blob of hydrogen. So all the atoms that exist are due to the fusion reaction that's constantly going in the sun and in our stars and in the solar system.
It's really a process that generates massive amounts of energy per unit fuel. So that means that it really is abundant energy that you would be able to get out of this.
The prospect of fusion is actually much better now than it was even 10 years ago. It suddenly turned into a factor in the fuel mix of future power in a way that I would not have said even just 10 years ago.
Fusion, which is like this golden child in the future that hasn't had to deal with any of the challenges that fission had. Fusion, I love. I think the fusion industry tries to throw fission under the bus a little too much by being like, no, we're not that thing. That's dangerous and messy. Like, we're great. But fusion is amazing, and I hope we get fusion power soon as well.
We're just in a glorious set of flowering Cambrian explosion of types of fusion power ideas. A decade ago, there were 10 serious fusion companies, and now there are over 45. I mean, it's really going.
Fusion power is cool. Fusion power is the sun, and all my other favorite stars. It's not really in doubt that it's physically possible. We just don't know how to do it. We're not smart enough. We haven't figured it out. We haven't put enough money into it yet.
I get a feeling that there really is something going on there, some physics that we don't understand. But the bottom line is very seriously that we don't understand.
A couple years ago, there was some really big news out of California. There's an experiment there called the National Ignition Facility, or the NIF. They actually fire a bunch of lasers into a capsule, essentially, and heat that capsule to intense pressures and temperatures. And then that capsule has a fusion event. So that's called inertially confined fusion.
NIF is a giant laser. It's over 400 megajoule of laser that deposits around a couple megajoules on a target. And then what happens essentially is just if you look at the energy deposited on a fusion target and think about it as the size of your pinky nail, a sphere that has fusion fuel, and that sphere, the energy deposited to implode that sphere was actually less than the energy the target produced. So after NIF demonstrated that fusion is possible, so now it's about a race of how do you make this commercial, which means making the unit economics work. How do you get it to be repeatable? So that means, you can fire at a point where you can have a baseload fusion power source, which is a really, really hard problem because we need to fire, one shot a minute or eventually one shot a second. So there's a significant, engineering challenges to get to a high repetition rate such that we can use fusion as a baseload power source. And then after that, you have to think about what we call Q commercial, which is, the commercial feasibility of the project.
If you want to make this a technology that gets out to the whole world, you have to make it economically competitive. Even if you get this to work and it costs 100 times more than electricity, nobody's going to sign up for that. So it has to be something that, even when you start, has to be close to the cost of electricity, what it is now.
And so fusion fuel is abundant. It's in deep sea water. It's safe. There's just no radioactive long-lived radioactive waste. It's on demand, so it's not geography dependent. You don't have to wait for the sun to shine or the wind to blow.
That, combined with the fact that you're not burning that much of it to emit energy. So compared to chemical reaction, is about 1 million times less efficient than a fusion reaction. So per unit of fuel, not only is the fusion fuel the most abundant fuel in the entire galaxy, it also happens to be the most efficiently burning fuel by like a factor of 1 million.
I think there's at least a couple more stages to go in the technology before you get to something you'd really want to try and run the world on, because of the fuel mix that they use in the best experiments now is a mixture of deuterium, which is fine, and tritium, which is not fine because it's radioactive and it costs $30,000 a gram. So you don't want that. You don't get no low fuel costs when you're using that.
Those numbers really matter when you want to make energy really abundant and really cheap, such that you don't have to worry about how much is your computer consuming or all those data centers need to operate, so we can power a futuristic civilization. And our mission is to accelerate the world's transition to fusion energy while safeguarding humankind. Fuse is working on a direct drive that already saves 10 times energy efficiency, which has been proven on the Z machine. Fuse, the Titan technology, is the highest efficiency driver ever built, going from 30 to 40%, which is what current pulse power architecture energy efficiency is, to over 89%, which is what we've experimentally demonstrated and peer-reviewed on our machine.
My name's Brandon Sorbom. I'm the Chief Science Officer and one of the co-founders of Commonwealth Fusion Systems. A tokamak is essentially a lot of very, very strong magnets arrayed in a donut shape. So the science behind tokamaks is probably not super widespread as far as something that people learn in school, but it's actually been studied quite extensively over the past 50 years. So as far as the science is concerned, we actually have a pretty good handle on it. It's really the engineering of this machine, making really, really strong magnets that can take that plasma and squeeze that plasma. And a big piece of our company in the early days was really proving out a whole new type of magnet technology that makes very strong electromagnets out of a device called a high-temperature superconductor. What we're trying to do is we're trying to create essentially a miniature star here on Earth in a tokamak. And we're building in this room behind me, we're actually starting to build that tokamak. And on our site, we also have a manufacturing facility that is producing a lot of the components that are going to be put into this device. Those magnets produce a very strong field that compresses this star, this plasma. So stars are made of a material called plasma. It's the fourth state of matter. And plasma is electrically charged, so we can use magnets to confine this plasma and to keep it safe from its surroundings, so the plasma can keep going and keep producing heat, which we can then take the heat out and convert it into electricity and send that electricity anywhere.
So right now, Titan that we built is a 1 terawatt driver. So 1 terawatt is roughly 20% of the whole world's power generation for a few nanoseconds, or equivalent to the whole Western Hemisphere power generation for a few nanoseconds. And so what we use Titan is not a fusion machine on its own, but it's essentially the pulse power driver that would deliver the electromagnetic force required to implode and create fusion reaction. So we'll need on the order of like hundreds of Titan at machine scale that's producing power, like commercial power generation. What we need to drive down is the cost per joule delivered on target. So if you think of the objective of Titan as how can we reduce the cost of a joule that we deliver to a target, and then from there on, you can increase the target design efficiency such that you can increase your neutron yield, right? So there's two functions that are really important to optimize when you think of a fusion power output. One is how much does it cost you to deliver power on a target, and that's dollar per joule. That's what Titan is really focused on. And then the second point is on how much, what's the gain efficiency of your target. And right now, Fuse has demonstrated we have the cheapest and most reliable source for high repetition rate to deliver energy to a target. And then the next step would be on working on target designs that would essentially be high gain. And here on targets, there's significant work already going on national security by Los Alamos, Sandia, and Livermore on doing better and better target designs.
The other milestones that we are reaching as a company, right now we're building this device called Spark, a commercial prototype of the device itself that will make a bunch of fusion heat. So Spark is going to make over 100 megawatts of actual heat from fusion. That's a lot of power's worth to make in a device. And Spark is going to be the first commercially relevant net energy fusion device. So an exciting development in the last couple months is we've actually selected the site and secured the site for the first ARC power plant. And so this is a grid-connected site that is in Virginia that we will be building the first fusion power plant on that will provide fusion power to people. And we plan on building a whole bunch more after that. But it's really exciting, and it really speaks to how close this technology is that we've already secured a site that's connected to the grid to build this technology on. So this isn't something that's far off in the future. Like, this is happening right now.
I'm cautiously optimistic that we're going to get Mr. Fusion or something like it by the end of the century.
The long-term impacts of climate have been recognized probably for more than a century now in terms of emissions of CO2 leading to an increase in temperature. And there's been a series of big international meetings that have been set up to try and do something about CO2 emissions and climate change. The one that I first remember is the Kyoto Protocol. Essentially, at the governmental level or the United Nations level, all these protocols have failed to curtail CO2 production in any way. The only way they could have succeeded was by taking 90% of humanity and winding back the clock 100 years in terms of progress and poverty and so on. And that's basically the reason why they failed. Right? Like, no country is going to unilaterally or even multilaterally be able to force through the sort of policy changes necessary to push their economy in the direction of, say, North Korea. Improvements in efficiency and user efficiency and so on. You can reduce the total amount of energy you're using. You can reduce your personal climate impact, but reducing it by 90% it's just an ask that most people are not prepared to accept.
I think around the 1970s, we started to consume less energy, especially in the West. You look at cars in the 1960s and 70s, and I think you can actually see this in how cars look. I think cars started to become a lot less beautiful because we started to think about fuel efficiency. We started to think about fuel economy and using less energy, and cars became less of this beautiful thing that's very powerful and very fast and fluid. And it became more of a function of energy consumption.
But only really recently did we get wind power. If you look at before the 1990s, there's almost none in the US. And then it does scale up pretty massively. And then we had the same thing happen with solar power, but not until like the early 2010s before it became any sort of a significant percentage of the overall mix. And with those increasing sources, we have reduced our burning of coal as a nation. But for about the last 20 years, our total electric power production in the country has been approximately flat, while I think population has grown. So that could be read as like we're becoming more efficient, but also we are certainly using electricity to do transport now with battery electric vehicles, which is like fundamentally changing what that total energy mix can be. And you basically have residential, industrial, and transport uses.
I think when humanity tries to consume less energy and it gets into a mindset of energy conservation, our lives start to be a function of that in not a very beautiful way. And in the reverse, when you're in an abundant era of energy, things become beautiful. You're not necessarily concerned about these marginal use cases of energy, and you really just make what you want.
We should certainly not limit ourselves from using energy to better our lives.
It's an interesting challenge, and two things can be true at once. Energy can be the root of all things good, and it can also have negative externalities, such as a changing climate as well. Then that's the problem to solve.
It appears to me that the impact, particularly on the developing world, of pushing our technology back to the point where hunger wasn't largely a solved problem, for example, is actually far worse than the impacts of climate change, even under the worst case scenario. Worst case scenario for climate change is something like coastal cities get drowned, a lot of places have increased food insecurity, but overall the world is still a net producer of food. It's a major pain in the ass and a big problem for our children and grandchildren, but it's not as bad as 6 billion people starving to death in the next 10 years. Bad, right? We have to keep these in perspective.
The key thing is to turn the conventional wisdom around so that people realize that energy is not only their friend, but their planet's friend.
I would say that energy is actually the solution to all of the problems that you think of when you think of the environment and you think of the human condition and taking care of the earth. I mean, just a good example of this is carbon in the atmosphere, right? We're slowly pushing up the amount of CO2 in the atmosphere over time. Everybody realizes this is an issue. Eventually, we're going to reach levels of CO2 which are not conducive to human life. But with enough energy, you can literally just suck it out of the atmosphere. With enough energy, we can reformat, oceans to make them habitable for the types of species of fish that we want to see. With enough energy, we can desalinate water, and we can re-aerate massive portions of desert and make them beautiful and make many more species flourish in them. All of these problems are actually functions of energy consumption. So if we give ourselves the ability to consume a lot more energy, we actually get to go fix a lot of these problems that seem intractable today.
So I think there's two places that the idea of consuming less energy comes from. One is sort of old school environmental movement. To a lot of people, that means doing less, by extension, consuming less energy. And then I think more, in a more modern context, a lot of times it's certain types of climate activists who associate energy with fossil fuels, and they want us to use less fossil fuels, but that means more generally less energy, and that's the thing that will help the climate.
We cannot afford new oil and gas. It is going to take everything we know and love. The cost of living crisis is part of the cost of oil crisis.
Anyone who thinks that the limitation of energy is a good idea is totally ignorant as to the role that energy plays in everyday life, or evil and trying to just hoard it for themselves.
The environmental movement, Club of Rome paper, and this whole kind of Paul Ehrlich movement within the environmental movement that was not just we want clean energy, but more energy is bad because human growth and flourishing is bad. And I think Paul Ehrlich, the population bomb guy, said that giving humanity more power is like giving an idiot child a machine gun or something to that effect.
The environmental movement, which really got going in the 1970s in the US and globally, really took such a short-sighted, a very small-minded, frankly, view of it. But I understand where it's coming from, right? They were sort of afraid of a society that was getting rid of conservation. We weren't going to have beautiful natural landscapes anymore. But they're not at odds with energy usage at massive scale, which provides for technology breakthroughs, that provides for prosperous societies. We can do them in responsible ways. We can do them in beautiful ways. And I would love to see us have both. Let's have beautiful landscapes, let's have conservation, while we also have industry and we have, a society that everyone can be prosperous in.
As a species, as humanity, right, on our whole planet, I think it's inarguable that you could say that if the average person had more energy, their life would improve.
You look at the developing world and countries that have not yet reached the US levels of prosperity, well, guess what? They also don't have the US levels of energy consumption and energy access. So you can see it around us it seems like we see this strong correlation of energy with human flourishing.
I think it would be a massive step backwards to consume less energy per capita. Limiting ourselves from a materials standpoint, certain industrial processes manufacturing aluminum is energy intensive, and not being able to have that material would harm our life in countless ways.
We have a whole other half of the technologies that we might have had that we didn't get because of the reliance on energy and the fact that we flatlined. For 50 years, we have been a 10 kilowatt society, 10 kilowatts per person, and the total amount of energy that the society has used has gone up, but that's because the population has increased. So the energy per person is still at about 10 kilowatts.
So I'm more a fan of abundance. How do you create energy abundance, and how do you actually make more resources available in a more abundant way? Tapping into those exponential growth curves is way more important for civilization and progress versus trying to stay at where we are or go down below.
Does anyone actually believe that we would have wars if resources weren't a constraint? My thinking is that by providing enough access to energy, by making resources infinitely available, making it so people don't have to think of land as something that needs to be conquered in order to gain access to these resources, I think we could end war on planet Earth.
Energy has really set the tone for geopolitics in the 20th century. Who has the oil, who can refine it, who can move it around. This is a tool that I think we figured out pretty early in the 20th century was going to shift the scales of power throughout the world. And for a long time, America recognized that we need that. We need that dominance. We need to be able to produce our own fuel, to export our own fuel. I think we kind of got lost in the 70s, though. We decided that, oil is bad, that it's running out, that it's affecting the environment. And then rather than finding solutions to that problem, we essentially tried to push oil away, right? We tried to push it to other places to be drilled and other places to be refined and slowly shift away from it. And I think that really negatively affected our position in the world too. And it caused us to get involved in conflicts over where that oil was coming from when we actually had a lot of natural stores of it here.
I think it's certainly true that most of the world's armed conflict was largely led by resource scarcity.
That could be space, it could be materials, it could be water, it could be power directly. But if essentially that you're able to allow different cultures to thrive within their own context without having to butt up against each other, without having to try to feel like they're in a constrained environment where violence is the only solution, if you're able to just take that out of the picture, the idea of killing each other by the tens of thousands or millions, that's what I think we can really put to end by making resources just fundamentally available to everybody.
Process of the Industrial Revolution is not stopped, it's keeping going, and nowhere is this more obvious than in computers. If you look at your iPhone, you have more computing power in your hand than the Navy had in 1980.
Energy abundance, I agree, is not necessarily obvious, mostly because we take energy for granted. We don't see it, feel it, live it in our day-to-day.
I don't like the word consume more electricity. I think efficiency is important. But we shouldn't stop what we're doing and go focus on efficiency. We also shouldn't try to just scale up consumption. We should try to do great things, right? To go places we've never gone before, to really understand our place in the cosmos. And we shouldn't ever be limited by energy. We should increase our production of energy, pacing population growth. Every time there's a massive efficiency boost, that's a big gain and benefit. And we should be spending to make that happen.
Right now, something like 50 million people worldwide enjoy the benefit of being able to jump on a plane, fly around the world. This is an incredible privilege. So if we 10x the amount of energy being consumed in aviation, right off the bat, that's 500 million more people are able to fly. So basically you take that curve, you lift the ceiling, and everyone else gets brought along behind. And maybe that one day we'll have a world where 8 billion people can jump on a plane and fly around.
I think abundant energy on Earth would solve many of Earth's problems here today. If you have enough energy, you can fix the environment. You can remove carbon from the atmosphere. You can create habitable environments for species that are threatened. Being able to actually produce hydrocarbons cheaper than you can refine oil is probably the most important technological unlock of the 21st century. If we can actually produce abundant hydrocarbon fuels outside of oil and gas, we would literally decarbonize the entire economy overnight.
The kind of projects that we could build as a culture are just expanded immediately. We could begin to actually do the space things that we had thought about in the 60s, thought we were going to be doing soon. We could actually go and try and colonize Mars, for heaven's sake.
I think, an energy abundant future means that we have access to technologies that today only the very, very few elite research institutions or noble missions have access to. So that means the rate of technological progress will accelerate at orders of magnitudes that we have not seen before. The level of infrastructure required for basic human functioning and for us to integrate technology in our daily life will just become, something we don't think about.
If you have unlimited quantities of cheap energy, it is crazy to do anything else, right? Because then you can literally start with any raw material you like. Like right now, if you want to create humans, first of all, you have to start with a bunch of hydrogen, and then you have to collapse it into a star, and then you have to form a planet nearby. No, wait, there's another step. That star has to die and produce more elements that then explode outwards. And then they have to come back together and form another star and a bunch of planets. And then those planets have to get life. And then the life has to chug along for a while and eventually absorb photons for a few billion years and then emit a Tesla and some people and stuff like that. But if you have infinite energy or the ability to to transform between different kinds of energy in effective ways, you can literally start off with hydrogen or rocks or anything you want and convert it to any other thing you want.
I do think you can imagine a world where things, you're living in spaces that are extremely high functioning, dense, clean. Think of all the jobs you could have robots doing. You can free up humans to work on other creative pursuits. And I think that that's, a beautiful world where humans can be doing what humans do best and leaving some of the rote labor to energy can power those sorts of technologies, robots and other things.
I think the future of humanity as we go forward is sort of like a conductor or a composer. So if you think of AI at your fingertips, even now with ChatGPT and some of these LLM models, you can sort of tell them to start doing things, and directing them generally on what you want them to do. And that costs a lot of energy. So we need to produce a lot more energy. But as these things advance and as it starts getting connected to robotics, you begin to actually craft narratives about how you want the physical world to look. And the AI does it for you, and it consumes energy and it uses robotics. And we become sort of these conductors or these artists with the physical world as the canvas and outer space as the canvas. And we create these beautiful cities, I hope.
I think that looking back on a more cosmic timescale, on a geological timescale, we're going to explode off this planet. And that's going to create a much bigger sphere of influence for humans, a much bigger place for us to use energy, a much bigger place for us to explore, to enjoy, to satisfy our curiosity. And energy is going to be a part of that story. We're going to have nuclear powered rockets, zipping around the solar system so that, we don't have to wait for the planets to line up and launch to Mars every 2 years. Just go anytime you want.
Space travel is interesting to me. I guess I'm more interested in what you do when you get there than I am at the propulsion aspect of it. So for the moon or for Mars, I'm really interested in megawatts of power, harvesting and bringing resources up and producing things. So Mars is this planet where the surface layer is just dust that's been mixing for a few 100 million years. It's all really random, right? It's all mixed up with itself. So it looks the same wherever you go and you measure it. But a couple of places we found, I think there was actually just a nearly totally pure sulfur rock found on Mars. And one of our rovers had locked its wheel, I think the Spirit rover, and it dragged this wheel and uncovered this bright white patch that it found on its mast cam. And so the NASA scientists had it go back and take a sample, and they found 96% purity silicon dioxide on the surface, which is glass. I want to see construction vehicles, and those need power too. So maybe even more than propulsion, I'm more excited about big machines, moving big amounts of material and mining, producing millions of tons of goods at really high purities, which maybe is the ultimate measure of how civilized a planet is.
I think with infinite energy, definitely, I think we can become a multi-planetary species. That's just because, now we can power things, ideally, if they're location independent, and you can, go to the moon and go to Mars and build energy bases and power all the research and technology required to get there. So, I'm very excited about that.
We're manufacturing in space. We're colonizing celestial bodies. Our ability to travel between those celestial bodies is accelerated. Even here on Earth, our ability to traverse the Earth accelerates by a factor of 10, that is. What if we had commercial hypersonic travel available to us today? You could even imagine a world where we use space launch as a way to navigate the Earth, right?
There is antimatter. There are antimatter particles that humans can generate through known sets of physics reactions, including some of those that occur in a fission reactor. So a 3.5 megawatt thermal reactor generates about 27 kilowatts of antimatter continuously while operating, antineutrinos that shoot off through the Earth and everything else and just go out into the forever of space.
There's the concept of an O'Neill cylinder, for instance, is this really fascinating thought experiment, which is, what if you created a giant floating cylinder out in space and rotated it at the right speed to create artificial gravity and pointed it at the sun so that you have some sunlight coming in? And could you create a human civilization that's essentially floating out in space? And what's interesting about that is it's somewhat infinite, right? If you can create one O'Neill cylinder, you can create 1,000. And what do each of those do? Well, they have factories inside, and the factories are producing things, but they're not using human labor, they're using robots. And those robots are consuming energy from nuclear reactors. Once you start to really understand the constraints of that system, you can see that it's truly infinite. As long as we have access to energy and as long as we have access to physical material, we can truly create whatever our minds imagine. And that's a very exciting future to me.
And like many of my peers in the space that are very excited about space travel, I'll let them have fun with that. That's not my thing. I like to think about just like, how can we make life on Earth so comfortable and so luxurious for everybody? And so that involves just 10xing so many of these things that we think of as normal in upper society, but that other people still don't have regular access to. And so that's really where my focus is.
The really exciting thing for me about this is that it allows us to be even less thoughtful, even more productive when it comes to performing the processes that we need to interconvert between different kinds of matter. So like right now at Terraform, we are sweating bullets trying to figure out how to convert sunlight and air into fuel at a price that makes sense for our consumers. Right? It's like, if it was easy, people would have done it. It is just possible. But if energy is 100 times more abundant and 100 times cheaper, then we don't have to be quite as careful in how we use it.
The bottom line is, I'm looking at another industrial revolution that multiplies everybody's standard of living by another factor of 100.
As long as we have access to energy and as long as we have access to physical material, we can truly create whatever our minds imagine.
Energy is going to be a part of that story.
Energy is what makes us human.